To truly understand a great cup of coffee, one must first look at where the story begins, with the raw, unroasted coffee bean. It doesn't smell like coffee at all. This green coffee consists of the dried seeds harvested from the fruit of the coffee tree. Visually unimposing and smelling faintly like raw plant material or dry straw, these seeds bear almost no resemblance to the aromatic beverage enjoyed around the world. At this stage, tasting or smelling the seed yields none of the familiar, rich, complex flavors associated with a freshly brewed cup. All of that sensory complexity is dormant, waiting to be unlocked through a process of heat-driven transformation. It is a remarkable metamorphosis, as a dense, raw seed with virtually no appealing aroma is coaxed into releasing hundreds of distinct, highly prized flavor compounds. At its core, the roasting process relies on a delicate balance between three distinct flavor characteristics: bitterness, acidity, and origin traits. As the roast progresses, bitterness steadily increases. Much like melting sugar into a dark caramel, a longer exposure to heat naturally yields a deeper, more bitter profile. Acidity follows a very different trajectory, rising early in the roast before reaching a peak and gradually diminishing as the bean darkens. This declining acidity explains why many consumers naturally gravitate toward darker roasts, which offer a smoother, less sharp cup. However, in the realm of specialty coffee, preserving the third element, origin characteristics, is paramount. The specific soil, altitude, regional climate, and post-harvest processing methods impart a unique chemical footprint to each lot of coffee. Lighter roasts retain these distinct regional nuances, whereas prolonged roasting eventually masks them under a dominant, generic taste of charred wood and heavy toast, rendering beans from vastly different origins virtually indistinguishable. Following the physical journey of a bean inside the roasting machine reveals a dynamic sequence of biological and physical shifts. Initially, during the dry end phase, the green coffee absorbs thermal energy to evaporate its internal moisture, shifting in color from muted green to pale yellow, while releasing a smell akin to warm hay. As the internal water turns to trapped steam and carbon dioxide builds up, internal pressure rises rapidly within the cell structure. This pressure buildup eventually reaches a threshold known as first crack, where the bean physically expands and bursts open with a sharp, distinct popping sound, reminiscent of popcorn. This pivotal moment signals the true onset of rapid browning reactions and complex chemical transformations. From first crack onward, minor shifts in roasting duration or heat application yield dramatic changes in acidity, sweetness, and overall flavor balance, transforming a once tough seed into something genuinely soluble and delicious. If the roast continues past this initial balanced stage, the physical structure of the bean undergoes further dramatic changes. The surface smooths out, the deep wrinkles disappear, and the color deepens into a rich, dark brown. Eventually, the internal pressure builds to a second threshold, known as second crack. At this late phase, the structural matrix of the bean fractures further, becoming porous, expanding significantly in volume, and losing density. The intense internal pressure forces natural coffee oils up through the pores to coat the exterior surface with a glossy sheen.
The longer the heat is applied beyond this point, the more the original, fruit-like acidity and regional personality dissolve, replaced almost entirely by deep bitterness and a heavier body.
Understanding what labels like light, medium, or dark mean requires recognizing that specialty coffee roasters and commercial high-volume roasters operate on slightly different scales. In specialty coffee, light roasts occupy a wide band that begins shortly after first crack, prioritizing vibrant acidity and distinct origin character. A specialty medium roast pushes slightly further into warmer brown tones, while the appearance of any oil on the surface generally marks the boundary into dark roast territory. Commercial roasters, by contrast, shift these boundaries further down the thermal spectrum, often roasting considerably darker to achieve a uniform, predictable flavor profile across massive batches.
Yeah, tell the Columbia warehouse to expedite the next bean shipment. We're falling behind.
Only the finest harvest will do for my morning brew. Perfect roast, impeccable quality.
Furthermore, when a bag carries an espresso label, it rarely dictates a mandatory brewing method. Instead, it signals that the roaster developed the profile, often through a slightly longer roast time, to make the coffee more soluble and easier to extract under the high pressure and brief contact time of an espresso machine. Achieving a precise flavor profile requires far more than placing green coffee into a fixed temperature oven. Simple static heating leads to uneven conduction marks, scorched, flat-tasting coffee. Modern coffee roasting relies on precise thermal control, a craft recorded as a roast profile. Using multiple probes positioned throughout the machine, roasters measure the real-time temperature of the beans, making minor adjustments to gas burners and airflow to carefully guide the heat absorption rate. Because modern consumers expect coffee to be packaged and shipped almost immediately after roasting, quality control teams rely on objective data checks alongside routine tasting. They track total roast loss, the percentage of weight lost during roasting, primarily from water evaporation, and use specialized spectrophotometers to measure the surface color using standard scales like Agtron. These combined metrics ensure that every batch hits a precise target window before it leaves the roastery. The physical machinery used to roast coffee generally falls into three primary technological designs, each transferring heat through a different combination of conduction, convection, and radiation. The most classic equipment in specialty roasteries is the traditional drum roaster, where coffee tumbles continuously inside a rotating metal cylinder over a heat source. In a drum roaster, hot air pulled through the chamber supplies convective heat, while direct contact with the hot metal drum provides conductive heat, yielding a rich and complex cup profile. Once the desired target temperature is reached, the beans are instantly discharged into a cooling tray, where high-powered exhaust fans and occasionally a minute mist of water, known as quenching, rapidly lower the temperature to halt the roasting process. In contrast to traditional drum designs, hot air roasters, often called fluid bed roasters, suspend and agitate the coffee beans entirely on a continuous cushion of heated air. By eliminating direct contact with hot metal, these machines rely exclusively on convection, which many roasters prefer for producing clean, bright flavor profiles with exceptional clarity. Finally, hybrid roasters combine these approaches by utilizing a rotating drum to agitate the beans,
while relying on an external heat exchanger to heat the air, preventing the drum walls from reaching high temperatures.
Ultimately, whether utilizing conduction-heavy traditional drums, high airflow fluid beds, or modern hybrid systems, these machines serve as precise mechanical tools, enabling the roaster to sculpt the final taste, texture, and aroma of the coffee bean.